Preparing for a nuclear instrumentation engineering interview. You've reached Candy Mentor, and this video is for you. We'll walk through 15 key questions you're likely to face. For each question, you'll see a sample answer, followed by the key points to cover. Subscribe, like, and share, and drop a topic request in the comments. Question 1. How would you choose between a gas-filled detector, scintillation detector, and semiconductor detector for a nuclear measurement application? I choose the detector based on what I need to measure and how accurately. Gas-filled detectors are rugged and good for area monitoring or contamination surveys, but they have limited energy resolution. Scintillators like NAITL give high efficiency and fast response, useful for gamma counting. Semiconductor detectors, especially HPGE, provide excellent energy resolution for spectroscopy, but need cooling and careful handling. So the best detector is driven by resolution, efficiency, environment, and maintenance constraints. While answering, focus on detection mechanism, energy resolution, efficiency, count rate capability, ruggedness, cost, operating voltage, and whether the application means survey monitoring, spectroscopy, neutron detection, or precision laboratory analysis. Question 2. Explain the signal chain from a radiation detector to the final digital count or spectrum. A radiation event first produces charge or light in the detector. That signal is converted to an electrical pulse, usually by a preamplifier or photomultiplier. The shaping amplifier improves signal-to-noise ratio and creates a pulse suitable for measurement. A discriminator rejects low-level noise, and an ADC or multichannel analyzer converts pulse height into a digital channel. For spectroscopy, pulse height corresponds to deposited energy, so stable gain and low noise are critical. Make sure to cover charge generation, preamplifier function, shaping amplifier, discriminator, ADC or MCA, pulse height relationship to energy, timing considerations, and how noise affects measurement quality. Question 3. How do you perform energy calibration and efficiency calibration for a gamma spectroscopy system? Energy calibration maps NCA channel numbers to known gamma energies using certified sources such as CS137, CO60, or EU152. I identify clean photo peaks, fit channel versus energy, and verify linearity across the range. Efficiency calibration is different. It relates counts in a peak to actual emitted photons using source activity, branching ratio, counting time, and geometry. The key is keeping source-to-detector geometry consistent and documenting uncertainty, background, dead time, and calibration validity. In your answer, talk about known calibration sources, peak identification, channel-to-energy fitting, absolute versus relative efficiency, geometry consistency, source certificates, uncertainty, background subtraction, and periodic verification. Question 4. What are dead time and pulse pileup, and how do they affect radiation measurements? Dead time is the short period after one event when the system cannot correctly process another event. At high count rates, this causes undercounting. Pulse pileup happens when two events arrive close together and their pulses overlap, often creating false higher energy counts. I manage it by reducing source intensity, increasing distance, optimizing shaping time, using pileup rejection, and applying validated dead time correction. If dead time is excessive, I treat the measurement as unreliable rather than just correcting blindly. Be sure to mention parallelizable versus non-parallelizable models, high count rate effects, undercounting, distorted spectra, pileup rejection, dead time correction, shaping time trade-offs, and how to validate measurements. Question 5. How would you identify an unknown gamma-emitting radionuclide using a measured spectrum? I would first confirm the spectrum is properly energy calibrated and subtract or compare background. Then I would locate statistically significant photo peaks and match their energies to a radionuclide library. I would not rely on one peak unless it is very distinctive. I would check expected secondary peaks and relative intensities. I also watch for Compton edges, escape peaks, and coincidence effects. A good identification combines energy match, intensity consistency, detector resolution, and sample context. While answering, cover background subtraction, energy calibration, photo peak detection, library matching, branching ratios, coincidence summing, escape peaks, Compton continuum, resolution limits, and confirming identity using multiple peaks. Question 6. What methods are commonly used for neutron detection, and why are neutrons harder to detect than gamma rays? Neutrons are difficult because they are uncharged, so they do not directly ionize matter like charged particles. We detect them indirectly through nuclear reactions or scattering. Thermal neutron detectors often use He3, Bf3, boron-lined tubes or Li6 materials, usually with moderators to slow fast neutrons. Fast neutron systems may use organic scintillators and pulse-shape discrimination. The challenge is separating neutron response from gamma background while maintaining efficiency, safety, and practical detector availability. Make sure to cover indirect detection, lack of charge, moderation, thermal neutron capture, He3, Bf3, Li6, boron-lined detectors, scintillators, gamma discrimination, and application-specific detector choice. Question 7. How do you apply ALARA principles when working with nuclear instrumentation in the field? ALARA means I plan the job so exposure is as low as reasonably achievable, not just below limits. I minimize time near sources, maximize distance, and use appropriate shielding. Before work, I check permits, dose estimates, survey data, and instrument readiness. During work, I monitor dose, control contamination, and follow source handling procedures. If readings differ from expectations or controls are not in place, I stop and escalate. Good instrumentation work is inseparable from radiation safety. In your answer, discuss time, distance, shielding, work planning, source control, dosimetry, contamination checks, survey meters, interlocks, job briefings, permits, and when to stop work. Question 8. Describe the purpose of source range, intermediate range, and power range instrumentation in a nuclear reactor. Reactor neutron flux changes across many orders of magnitude, so one instrument range cannot cover everything accurately. Source range instruments monitor very low flux during shutdown and startup. Intermediate range covers the transition as power increases, often using logarithmic indication. Power range instruments monitor normal operating power and support protection functions. The ranges overlap, so operators can cross-check readings during transitions. Calibration, channel redundancy, and reliable trip logic are essential, because incorrect flex indication can affect reactor safety. Be sure to mention reactor startup monitoring, neutron flux range coverage, detector types, overlapping channels, logarithmic versus linear response, protection functions, calibration, and safe transition between ranges. Question 9. What are common noise sources in nuclear instrumentation, and how would you reduce them? Noise can come from the detector, high voltage supply, preamplifier, cabling, grounding, and nearby electrical equipment. I reduce it by keeping the preamplifier close to the detector, using low noise cables, proper shielding, single point grounding, stable bias supplies, and clean power. For spectroscopy, shaping time must balance noise reduction against pileup. I also check for microphonics and loose connectors. My approach is systematic. Isolate each stage and verify signal quality with known test pulses or sources. While answering, focus on electronic noise, leakage current, microphonics, EMI RFI, ground loops, cable capacitance, shielding, filtering, detector bias stability, preamplifier placement, and signal-to-noise optimization. Question 10. How would you troubleshoot a detector system that suddenly shows 0 or very low counts? I would troubleshoot from the simplest and safest checks first. I would verify the source, geometry, acquisition settings, live time, and whether the instrument is in the correct mode. Then I would check high voltage, interlocks, cable connections, preamplifier power, discriminator threshold, and DAQ communication. If available, I would inject a pulsar signal to separate electronics failure from detector failure. I would avoid changing many settings at once because that hides the real root cause. Make sure to cover source and geometry verification, high voltage, cable continuity, preamplifier output, discriminator threshold, DAQ settings, detector damage, background checks, interlocks, and safe troubleshooting sequence. Question 11. What factors determine the high voltage setting for a radiation detector? The correct high voltage depends on the detector type and its stable operating region. For a GM tube, I look for a plateau where count rate is relatively insensitive to voltage. For scintillation systems, voltage controls photomultiplier gain and affects energy calibration. For semiconductor detectors, bias supports charge collection, but excessive voltage can raise leakage current or damage the device. I set voltage using manufacturer guidance, plateau or performance tests, stability checks, and documented configuration control. In your answer, discuss detector operating region, plateau curve, gas multiplication, PMT gain, leakage current, stability, manufacturer limits, noise, resolution, safety margins, and effects of overbiasing. Question 12. How do ADC resolution and multi-channel analyzer settings affect spectroscopy performance? ADC and MCA settings determine how analog pulse heights are digitized into channels. If the channel count is too low or the gain is poorly set, peaks become compressed and resolution is wasted. If the range is too narrow, high-energy peaks may be off-scale. I select settings so the energy region of interest uses enough channels without over-specifying meaningless resolution. I also consider conversion time, throughput, dead time, and stable gain, because digitization cannot fix poor analog signal quality. Be sure to mention channel count, energy range, gain, peak shape, resolution versus bin width, live time, ROI setup, conversion time, throughput, and avoiding overcompressed spectra. Question 13. How would you qualify nuclear instrumentation for use in harsh plant environments? I qualify instrumentation by proving it can perform its safety or monitoring function under expected service conditions. That includes temperature, humidity, vibration, radiation dose, EMI, seismic requirements, and aging effects. I review equipment qualification documentation, installation constraints, cable ratings, calibration drift, and surveillance test intervals. For safety-related channels, traceability and configuration control matter as much as technical performance. A device that works in a lab may still be unacceptable if it cannot survive the plant environment. While answering, cover temperature, humidity, radiation dose, seismic, EMI, aging, environmental qualification, redundancy, cable routing, maintainability, surveillance testing, traceability, and compliance with plant procedures. Question 14. What quality assurance and regulatory practices are important for nuclear instrumentation work? Nuclear instrumentation work must be technically correct and auditable. I follow approved procedures, use calibrated equipment traceable to recognized standards, document as found and as left conditions, and maintain configuration control. If a result is out of tolerance, I do not just adjust it. I evaluate impact and initiate the required non-conformance or corrective process. Depending on classification, independent verification may be required. The mindset is simple. If it is not documented, it is not defensible. Make sure to discuss calibration traceability, documented procedures, configuration management, independent verification, non-conformance handling, safety classification, records, audits, corrective actions, and standards such as IEC, IEEE, or site-specific requirements. Question 15. How would you design a reliable radiation monitoring channel for a safety-critical application? For a safety-critical radiation monitor, I start with the required function. What radiation type, range, response time, accuracy, and alarm action are needed. Then I select a qualified detector and electronics chain with redundancy where required. I design for fail-safe outputs, self-diagnostics, stable power, clear alarms, and maintainable calibration. Thresholds must avoid nuisance alarms, but still protect personnel or equipment. Reliability comes from the full system: sensor, electronics, software, procedures, testing, and operator usability. In your answer, talk about detector selection, redundancy, fail-safe behavior, diagnostics, alarm thresholds, calibration, environmental qualification, power backup, communication integrity, cybersecurity of networked, maintenance, and human factors. If you are still with us, congratulations. You are much ahead of the rest and serious about preparing for your interview. We hope we were able to add value to your preparation and create some helpful content. Do not forget to like and share this video. Your small act can do great things for us.